Hello everyone, in this video, we're going to talk about three important ideas in calculus: the directional derivative, the gradient, and tangent planes. To start off, let's say we have the following scenario. Suppose z equals f of xy is a surface and AB is a point in the domain of f. We know that the partial derivatives f sub x, f sub y, both evaluated at AB give the slopes of tangent lines at AB on planes parallel to the x-axis and the y-axis. Say, for example, we have the surface z equals f of xy equal to 9 minus x squared minus y squared, which is a paraboloid. And let's consider the point 1, 1, which is a point on the domain of f. Now, to compute for the slope of the blue tangent line lying on the plane y equals 1, we simply compute for the partial derivative of f with respect to x evaluated at 1, 1. Since the derivative is negative 2x and x is 1, we simply have negative 2. So likewise, to get the slope of the blue tangent line on the plane x equals 1, which is a plane parallel to the yz plane, or we can say it's a plane in the direction of the positive y-axis, and we compute it as f sub y at 1, 1, which is negative 2 times y evaluated at 1, so negative 2 times 1 equal to minus 2. Now the question is, meron bang generalization itong konseptong ito? So in other words, if we have this arbitrary plane, this green plane, which is perpendicular to the xy plane, and which passes through the point 1, 1, so we can form this tangent line, the blue line, to the curve of intersection of this plane and the paraboloid. So you want to know how to get the slope of this tangent line. The generalization we're looking for is actually a special derivative called the directional derivative. And we define the directional derivative formally as follows. So suppose we have the direction, which is a unit vector u with components u1 and u2. Now the function is given by f of xy, and our point of interest is x naught, y naught. So we define the directional derivative of f at the point x naught, y naught along the direction vector, the unit vector u, with components u1, comma u2, denoted as follows. and is defined by the uh, following limit, provided that this limit exists. To understand this abstract definition of the directional derivative, we will consider special cases. And what are those special cases? First is when the unit vector u is equal to the vector in the direction of the uh, positive x-axis, or the vector 1, comma 0. So in this case, the partial of the directional derivative of f with respect to u will be given by limit of f of x naught plus h times 1. So x naught plus h u1, since u1 is 1, becomes x naught plus h, comma y naught plus 0, or simply y naught, minus f of x naught y naught all over h. And as h goes to 0, we know that this is exactly the partial of f with respect to x evaluated at x naught y naught. Now the second special case is when the unit vector is in the direction of the positive y-axis, or u equals j equals 0, comma 1. Then the directional derivative in this case will be equal to the limit of f of x naught plus 0, since u1 is 0, comma y naught plus h, minus f of x naught y naught over h as h goes to 0. And this is equal to the partial of f with respect to y evaluated at x naught y naught. So in other words, the directional derivative is a generalization of partial derivatives. Okay, geometrically, again, we think of the directional derivative as the slope of the tangent line on some special plane. So as shown in this figure, you can see the green surface and the plane intersecting the surface perpendicular to the xy plane, and the point of interest P, and then the blue tangent line. So the slope of that blue tangent line can be obtained by calculating the directional derivative of f in the direction of the unit vector u, evaluated at the point x naught y naught. Now, as special cases, we have the following. So when the unit vector u is equal to the vector I, then the directional derivative of f with respect to u is the same as the partial of f with respect to x. Likewise, if the unit vector u is equal to the vector j, then the directional derivative of f with respect to u is the same as the partial derivative of f with respect to y, evaluated at x naught y naught. To illustrate the definition of the derivative, we consider the following example. Let's say we want to find the directional derivative of f given by x squared plus 3y squared along the given unit vector, square root of 3 over 2, comma, minus 1/2 at the point 1, negative 1. So our x naught is 1, y naught is negative 1, u1 is square root of 3 over 2, u2 is negative 1/2. So substituting those variables in the definition of the directional derivative, we get this limit. And as h approaches 0, so simplifying the expression, and then taking the limit as h approaches 0, we will eventually get this number, which is equal to square root of 3 plus 3. So just like ordinary derivatives, we don't usually use limits to calculate directional derivatives. There's a more convenient way of computing them than by evaluating limits, and that is by using this concept called the gradient vector or the gradient field of a function. So we define the gradient of a function of two variables x and y, denoted by nabla f of xy, or you can say it's grad f of xy, as the vector given by fx, or partial of f with respect to x at xy, comma, partial of f with respect to y. So to see how the gradient works, let's do this example. So suppose we want to find the gradient of f of xy equal to x cosine y minus e raised to y over x at the point negative 1, 0. So first, we need to find the following partials: partial of f with respect to x and partial of f with respect to y, since this is the general gradient, or the gradient at any point xy. Now, partial of f with respect to x is given by cosine y minus e raised to y times negative 1 over x squared. Partial of f with respect to y is x times negative sine y minus e raised to y over x. Therefore, evaluated at the point negative 1, 0, the gradient vector we're looking for is the vector equal to cosine 0 minus e raised to y times negative 1 over negative 1 squared, comma, 0 minus e raised to 0 over negative 1. Or simply, the vector, the constant vector, 1 plus 1, so 2, comma, 1. We will now give the formula for the directional derivative using the gradient of the function at the point xy. So here we have a differentiable function f and a unit vector u, Now, to find the directional derivative of f, we simply compute the dot product given by gradient of f or grad f dot the unit vector. So for example, suppose you want to find the directional derivative of the function in the previous example at the same point of interest, negative 1, 0, but along the vector 4, negative 3. Now we've seen that the gradient of the vector f at the point negative 1, 0 is equal to the vector 2, comma 1. But note that the given vector 4, negative 3 is not a unit vector. But we can uh, normalize this vector for negative 3 by dividing the vector by its magnitude, which is equal to square root of 4 squared plus negative 3 squared. So the unit vector, the same as in the same direction as the given unit vector, is equal to the vector 4 over 5, comma, negative 3 over 5. So therefore, the rate of change of f, or the directional derivative of f at the point negative 1, 0, is equal to the dot product of the gradient at negative 1, 0, which is equal to 2, 1, and the unit vector parallel to 4, negative 3, which is 4 over 5, comma, negative 3 over 5. So the dot product is a scalar. Note that it's a scalar, and it's equal to a sum of the products of first components and the second component. So we have 2 times 4 over 5, which is 8 over 5, plus 1 times negative 3 over 5, which is negative 3 over 5. So 8 over 5 minus 3 over 5 equals 1. And that is the rate of change of f at negative 1, 0 in the direction of the vector for negative 3. Now let me try to explain a little bit about the elegant formula for the directional derivative. This dot product formula for the directional derivative of f at xy. But first, let's consider the limit definition of the directional derivative. And that limit can be thought of as the derivative of f with respect to h evaluated at h equal to 0. Now, note that f is a function of x and y, where x is the first component given by x naught plus hu1, and y is the second component here, equal to y naught plus hu2. Now, each of these variables x and y is a function of h. So we have this diagram connecting these variables. So by chain rule, df dh is equal to partial of f with respect to x times the derivative of x with respect to h plus partial of f with respect to y times dy dh, evaluated at h equal to 0. Partial of f with respect to x, evaluated at h equal to 0, the same as fx at x naught y naught. Dx dh, on the other hand, is simply u1. Now, partial of f with respect to y is f sub y at x naught y naught when h is 0 times u2, where u2 is dy dh. In dot product notation, this can be written as fx x naught y naught comma fy x naught y naught dot the unit vector u1 u2. So finally, this is the same as grad f at x naught y naught dot the unit vector u square. Okay, it's quite easy to extend the idea of the directional derivative or the gradient field to functions of three variables. As you can see from these formulas or uh, definitions, you just need to add one component or one coordinate for the corresponding concepts. Let's do an example. So we have a given function f, this time a function of three variables, x, y, and z, a point of interest, which is 2, 1, 0, and a direction vector, which is 3, negative 4, 5, which is not a unit vector. So first, we need to compute for the gradient of f at any point x, y. So we know that this is equal to the three-dimensional vector fx, fy, fz, where fx is cosine z, fy is negative e raised to z minus 2y, and fz is negative x sine z minus y e z. So the vector grad f evaluated at the point of interest 2, 1, 0 must be equal to cosine. First component must be cosine 0, which is 1. Second component is negative e raised to 0 minus 2 times 1, so minus 3. And third component is sine 0 is 0, so we have 0 minus 1 e raised to 0, so we have negative 1. Next, we compute for the unit vector parallel to the given direction v. So we just normalize the given vector 3 minus 4, 5 by dividing the vector by its magnitude, Now the magnitude of this vector, p negative 4, 5, is simply square root of 50, since t squared plus 16 squared plus 5 squared is 50. So we have 3 over square root of 50 minus 4 over square root of 50 and 5 over square root of 50. Therefore, the rate of change of f at the point 210, so this is grad f dot u. So at the point 210, these vectors are 1, minus 3, negative 1, and 3 over square root of 50 minus 4 over square root of 50 and 5 over square root of 50. So the dot product is equal to this scalar 3 over square root of 50 plus 12 over square root of 50 minus 5 over square root of 50. Now 12 plus 3 is 15, so this is 10 over square root of 50 and this is 10 over 5 square root of 2. So finally we have square root of 2.